This is SpaceTime Series 29, Episode 35, for broadcast on the 23rd of March 2026. Coming up on SpaceTime, a monster black hole merger that sent ripples through space-time, a new type of ion propulsion system for spacecraft, and thousands watch as a fireball streaks across Ohio's skies. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected the merger of a pair of stellar mass black holes, which was quickly followed seconds later by a powerful gamma-ray burst. The event, catalogued as S241125N, occurred some 4.2 billion light-years away, sending ripples through the fabric of space-time. The merger, which was picked up by the LIGO, Virgo, CAGRA gravitational wave observatories, was unusual not just because of the extreme distance the gravitational waves were picked up from, but also because binary black hole mergers are not expected to produce electromagnetic counterparts, such as gamma-ray bursts. Gravitational waves are ripples in space-time from violent cosmic events. Gamma-ray bursts are the most powerful explosions in the universe since the Big Bang. So, S241125N could be a very rare gravitational wave event which has been linked to a gamma-ray burst across multiple wavelengths. Now, although the association has not yet been definitively proven and it will require further follow-up work, the probability of a chance occurrence appears fairly low, making the result statistically intriguing while at the same time warranting caution. Black hole collisions are thought to be dark to conventional telescopes because it was thought they emit no light. However, S241125N appears to defy that notion. About 11 seconds after the gravitational wave signal was received, NASA's Swift Space Telescope detected a short-period gamma-ray burst from the same patch of the sky. And shortly after that, China's New Einstein Probe Telescope found an X-ray afterglow in the same vicinity. The authors say the correlation between a gravitational wave signal, the gamma-ray burst, and the X-ray signal is unlikely to simply be coincidence. Their analysis, reported in the Astrophysical Journal, estimates the total energy, luminosity, and duration of the event appears to be typical for a short-period gamma-ray burst. There's one problem, however. The photon index is far softer than usual, meaning low in photon energy, and that implies the source may have a special radiation mechanism or a different propagation effect. One of the other striking aspects of the detection was its extreme distance. The gravitational waves travelled for some 4.2 billion light-years to reach Earth. That's a redshift of z equaling 0.73, meaning this collision occurred when the universe was significantly younger. The black holes involved were unusually massive. Analysis suggests the merging pair had a combined mass of well over 100 times that of our Sun, and that makes it one of the most massive stellar mass black hole mergers ever recorded. You see, most black hole mergers observed by LIGO involve totals of just a few tens of solar masses. So such a massive merger is rare and intriguing, and it hints that each of the black holes involved might themselves have grown from earlier mergers or from some sort of exotic formation process. The detection of a high-mass merger at Z0.73 also suggests that these events can be observed across vast distances. Hearing black hole mergers billions of light-years away and possibly seeing a flash from them is a remarkable achievement. The authors think the event may have been caused as two black holes merged inside a dense disk of gas and dust surrounding a galaxy's central supermassive black hole, an environment known as an active galactic nucleus disk. In these bustling galactic cores, enormous amounts of material orbit the central supermassive black hole, creating a fuel-rich setting. If a binary black hole happens to coalesce with such a disk, the merger doesn't occur in isolation. It happens amid a thick soup of material. And when the black holes merged, the newly formed black hole received a powerful kick or recoil velocity from the asymmetric gravitational wave emission. This kick black hole, now moving through the surrounding gas, would rapidly gobble up material in its path. And the accretion rate could be hyper-Eddington, far exceeding the normal limit at which a black hole can steadily consume matter, a figure known as the Eddington limit. And such intense accretion in a magnetized environment is thought to have triggered relativistic jets of energy and matter, launching out at superluminal speeds. As these jets ploughed through the heavy disk, they generated shock waves in the dense gas. Now, initially, the jet's energy was locked inside the disk, thermalizing the gas. But when the jets finally punched through the disk's surface, those photons could escape. The result, a burst of high-energy radiation surging out of the galaxy's nucleus. And this process would produce a short gamma-ray burst, not from a neutron star merger as is the usual case, but from a black hole merger in an unusual habitat. Such a shock breakout from the disk would produce a compromised gamma-ray spectrum, which intriguingly matches what Swift observed. The gamma-ray burst's prompt emission was unusually soft compared to typical short gamma-ray bursts. Now, if this gravitational wave and gamma-ray burst association is confirmed, it heralds in a new era of exploring black hole mergers using both ears and eyes. Until now, binary black hole mergers have only ever been heard through their gravitational waves. But S241125N suggests that under special conditions, they can also be seen in high-energy light. And that would provide rich opportunities to study the environmental conditions around merging black holes and the physics of how their jets form in dense media. Such a two-pronged measurement can even refine science's estimates of cosmic expansion by using the event as a sort of standard gravitational wave distance marker with an identified host galaxy redshift. This is space-time. Still to come, a new type of ion propulsion system for spacecraft, and thousands witness a fireball streaking across the Ohio skies. All that and more still to come on SpaceTime. This episode of SpaceTime is brought to you by Squarespace. If you've ever wanted to make your mark online, whether you're just getting started or ready to take your business to new heights, Squarespace is the all-in-one website platform specifically designed to help you stand out and succeed. I guess you could think of Squarespace sort of like a tidy roommate for your business. It handles all the scheduling crumbs, the unpaid invoices under the couch, and actually answers the door when customers knock. If you offer services, consulting, classes, events, whatever you call your expertise, Squarespace makes booking and getting paid straightforward. Built-in appointment scheduling, professional invoices, and secure online payments means you can spend less time juggling spreadsheets and more time doing what you love. And now for the showstopper, design. Squarespace's Blueprint A1 will sketch a fully customized site for you based on a few simple questions: industry, personality, goals, and then hand you a polished copy and layout to tweak. But if you prefer DIY, well, you can choose an award-winning template, drag and drop, and watch your brand grow from works in progress to stop the scrolls in just minutes. No coding tantrums required. And yes, people will actually find you. Squarespace's built-in SEO tools, that's meta description, auto sitemaps, and clean structure, help your site show up where it matters. So why not try it for free at squarespace.com/spacetime. And when you're ready to launch, use the offer code SPACETIME to save 10% off your first purchase of a website or domain. That's squarespace.com/spacetime and the promo code SPACETIME. And remember, you'll find the links in our show notes. Scientists are developing a new type of ion propulsion system for spacecraft which would be easier to produce and provide better performance than current xenon-based plasma propulsion systems. You see, instead of xenon, the new research centers around the use of iodine. Thousands of satellites are launched every year, and it's critically important to be able to maneuver those spacecraft once they reach orbit. And this is where onboard propulsion systems come in. Almost all propulsion systems used today are effectively classified as rockets. That means the system carries its own onboard propellant, and a thrust force is generated by ejecting this propellant away from the spacecraft at high velocity. Now, space propulsion typically uses either chemical or electric propulsion systems. Chemical propulsion systems, be they liquid-fueled or solid, provide an immense amount of power needed for launch into space. And while spacecraft in orbit still require fuel systems for critical maneuvers, they're limited by the amount of fuel they can carry. And that's where ion propulsion systems come in. They can provide sustained power for extremely long periods of time because they don't use much fuel. Ion propulsion systems use electrical power, typically generated from solar panels or stored in batteries, to accelerate their propellant using electric or magnetic fields. But there's a disadvantage. The force they produce is extremely weak. Put a sheet of paper on your hand, and that's roughly the force level that many electric propulsion systems provide. That's why ion propulsion can't be used to launch rockets or for emergency maneuvers in space. Because of its attractive properties, xenon has traditionally been the propellant of choice for many ion propulsion systems. However, xenon does present several challenges. It's a relatively rare gas, and production is through fractional distillation of air, a process that's both time-consuming and energy-intensive. For every 1,000 metric tons of oxygen produced, only about a kilogram of xenon is obtained. Consequently, xenon is expensive, costing around $5,000 a kilogram in today's money. And global production is also limited to around 50 to 60 metric tons a year. Current estimates suggest over 2,000 satellites are likely to be launched per year on average in the near future. That means demand for xenon will greatly outstrip its availability. And of course, this also ignores the demand for xenon from other sectors, such as the semiconductor industry, medical uses, and lighting industries. Also, Russia and the Ukraine produce about 30% of the world's xenon, and prices have surged significantly since Moscow's invasion of the Ukraine a few years ago. So this is where iodine comes in. University of New South Wales researcher Trevor Lafleur and colleagues have been looking into iodine as an alternative ion propellant. Lafleur says iodine is commonly found in antiseptics, table salt and pregnancy supplements, and it has many properties that make it attractive for use in space. It has a similar atomic mass to xenon and requires slightly less energy to ionize. That means it can achieve similar or even better performance. It's 100 times less expensive than xenon to produce, and global production is some 600 times higher. And that means it can meet both existing and future space demands. But iodine has its own problems. Being stored as a solid complicates how the propellant's delivered and the control of propellant flow to the thruster. Gaseous propellants can simply be directed to the thruster by opening a valve. However, iodine needs to be heated to just above 100 degrees Celsius first in order to allow it to sublimate, that is, transition from a solid state into a gas state without first becoming a liquid. Also, iodine is significantly more chemically reactive than xenon and can corrode many common materials such as iron and aluminum. So that means you're going to need special systems to manipulate it. Also, iodine has a very complex plasma chemistry compared to xenon, meaning that when you attempt to use it, many different types of reaction can occur. Still, currently there are already over 100 iodine electric propulsion systems in space, but most only operate at low power, below 100 watts, while larger satellites require up to 10 kilowatts or more to generate greater thrust. So these are the challenges that Lafleur and colleagues are facing.
So there's two broad classes of propulsion, chemical and electric propulsion. And at least for electric, the propellant of choice has historically been xenon, because it's a very noble gas. It doesn't react with many substances or materials, and it's got some very nice properties that make it suitable for propulsion. But there's a lot of change happening now in the industry, and so they're searching for some alternatives because xenon has a few challenges with it. One of those challenges is that it's quite expensive. It's quite a difficult gas to process, and so because of this and growing space industry demand, there's been a big push to look for some alternative propellants.
And that's where iodine comes in.
So iodine is an interesting substance. It has only, I would say, been considered as a propellant about 20 years ago, but that was too soon for technology, and it's only in the last 5 years or so that it's actually been demonstrated in space. Iodine is interesting because currently it's about 100 times cheaper than xenon, and global production sits at almost 500 times higher than xenon. So it can more than meet the growing space industry demand, and the cost is so low that it's particularly attractive. The other thing is iodine begins life as a solid, essentially, and so a solid usually has a much higher storage density than a gas like xenon, and so because of this you can have a much smaller propellant tank than you would need for xenon. And so all of these factors have made iodine an attractive emerging propellant, and so there's been a lot of research undertaken to try and develop technologies now to be compatible with iodine. And so, within the last 5 years, there's finally been some demonstrations of iodine in space, and now that it's shown that it can work, there's a lot of research going on to develop next generation propulsion systems and adapt other technologies to use iodine.
There are some challenges associated with using iodine. We'll get to that in a moment, but basically, how does an ion propulsion system work?
Actually, it turns out there's a whole zoo of different electric propulsion technologies, and one of them, at least the one that has so far been demonstrated in space with iodine, is something known as a gridded ion thruster, or sometimes just an ion engine. And basically, how this works is you have a chamber that you inject your iodine into, and then you turn that iodine into a plasma. And a plasma is basically like a soup of electrons and positive ions. And so what happens is you provide energy to this chamber and you strip electrons from the iodine atoms. And so you get left with this sort of soup of electrons and heavy positive ions. Then at the end of the thruster of the chamber, you have a set of grids with many little holes in them, and you apply a high voltage across these grids. And if you choose the polarity of your voltage correctly, you can extract and accelerate the positive ions and generate thrust in this way.
And what happens to the negative ones?
Good question. So this is one of the key points that has made iodine a bit challenging. If you just extract positive ions, then the thruster and the spacecraft would actually charge up negatively. And so all of these technologies usually need a second device called a neutralizer, which emits electrons, negative charges, that is to say, back into the exhaust plume of the thruster. And so in this way, you can maintain current balance, charge balance. The problem with iodine is it's very reactive with many common materials. And so some of the more advanced neutralizers, so far we have not successfully achieved stable operation with iodine.
Okay, so basically it makes things rust, I take is what you're saying.
Not quite rust, but it's very chemically aggressive. Many common materials like iron, copper, and even some aluminiums. And so it means you have to very carefully design your propulsion system. But for the neutralizer, most of the conventional neutralizers have a very special material inside that they use to operate. And so far, iodine seems not to be very compatible with this material. It causes a lot of erosion or chemical reactions, and so it shortens the lifespan. And often with electric propulsion systems, we may need these things to operate for thousands of hours just because of the duration of a space mission and so on. And as of today, the last numbers we've seen, I think some of the high-performance neutralizers have not been operated for more than 100 hours. So, yeah, there's a lot of challenges there with the neutralizer that still remain.
Is it difficult to transform a solid cake of iodine into a gas?
So far, no, but for high-power thrusters, that may be a challenge that emerges. At the moment, as I said, iodine begins as a solid, and luckily, if you heat the iodine propellant, it starts to sublimate, which is to say it transforms directly from a solid to a gas. And so as long as you control your temperature, you can control your sublimation rate and therefore your propellant flow rate. And so that's what's being done in all of the iodine propulsion systems that are currently flying. The problem is that for very high-powered thrusters, where you need a much higher flow rate, you can't keep doing this so easily, because once you heat the propellant above a certain temperature, it actually turns into a liquid first, and so that can cause some issues with your flow control and so on. There's a number of organizations working on technical solutions for this, so I have no doubt that will be solved. This is more a question of engineering rather than physics. But you do have to be a bit careful because, starting life as a solid, depending on your temperature and pressure, you might get turned into a liquid first before a gas. And so that's something we have to be aware of when we're designing these systems.
And the work you're doing, well, what does that entail?
Yeah, so I was originally in industry and actually was lucky enough to work on the first iodine gridded thruster tested in space. And then I left industry. I wanted to get back into academia, do some more fundamental research and education. And so I've taken some of that expertise with me, and we've set up a number of research projects to try and advance iodine propulsion. And so some of the work we're doing, for example, is associated with better understanding how iodine functions in these neutralizers so that we can help develop new neutralizers for the future. We've also developed now one of the most advanced iodine plasma chemistry models and understandings together with some of our collaborators in France. And so we're applying these chemistry sets and these models to help design new iodine propulsion systems, understand some of the basic physics because it's much more complicated than xenon. And as I said, to try and really push forward to develop feasible neutralizers to help make iodine propulsion much more widespread in the space industry.
Now, you mentioned earlier that most iodine engines that have become operational, they're only producing around 100 watts or less. What sort of propulsion figures are you needing?
Yeah, so the original iodine gridded thrusters, they were designed for CubeSats or small satellites, and so the power level only needed to be quite low. But if you look at space industry trends, the sort of kind of average mass of satellites now is sitting in the maybe 250 to 500 kilogram range. And so because the mass is so much higher, you also need a correspondingly higher thrust level. And that means you therefore need a higher power level. And so a good kind of target that a lot of people are looking towards is typically a few hundred watts, so maybe 500 watts or even as high as 1 kilowatt. And if you want to do some very advanced science missions, you may even need in multiple kilowatts or even tens of kilowatts. So low power has been nicely demonstrated in space. There's a lot of work that still needs to be done with high power, but that's probably where the future is because the needs of the space industry sit kind of like between the 500 watt to 1 kilowatt range.
Would you use this sort of a system for main propulsion or orbital maneuvering?
So up until now, the primary target has just been orbital maneuvers, and you would only have one of the systems. But on bigger satellites, you could potentially use clusters of these iodine thrusters, and if you synchronize the firing of different combinations, then you can achieve some so-called attitude control, which is to say you change the orientation of the spacecraft. And for bigger satellites, sometimes they even allow the thruster to articulate, which is to say they have something called a gimbal, which allows the thruster head, if you will, to swivel slightly, and so you can change the direction of your thrust vector when you fire the thruster. So in this way, you can enable a combination now of both large maneuvers to change your orbit and also small maneuvers to either change the orientation of your spacecraft or even very slight maneuvers to allow, for example, maybe proximity operations or formation flying or something like this.
That's Dr. Trevor Lafleur from the University of New South Wales. And this is Space Time. Still to come, residents across northeastern Ohio witness a spectacular daytime meteor streaking across the sky. And later in the science report, scientists may have discovered the region of the human brain responsible for controlling hypocrisy. Politicians and celebrities, watch out. All that and more coming up on Space Time. Residents across northeastern Ohio have witnessed a spectacular daytime meteor streaking across the sky. The morning fireball was spotted by thousands of people in areas from Wisconsin to Maryland. It was moving southeast at a velocity of over 20,000 meters per second before fragmenting over Valley City in Medina County. NASA says an analysis of currently available data places first visibility of the meteor above Lake Erie at an altitude of around 90 kilometers. They estimate it to be around 2 meters wide with a mass of about 7,000 kilograms. Witnesses in the Cleveland area reported hearing a boom and feeling the vibrations as the rock hit thicker layers of the atmosphere. NASA says fragments of the meteor continued southward, producing meteorites in the vicinity of Medina County. The agency says the asteroid unleashed as much energy as 250 tons of TNT as it fragmented, resulting in a pressure wave which propagated to the ground, causing the booms and explosive noises heard by the public. Actually, there appears to have been 2 explosions, an initial event over the centre of Lake Erie, followed by a second brighter explosion much closer to shore, possibly over the city of Cleveland or just west of the town. NASA's Meteoroid Environment Office lead, Bill Cook from the Marshall Space Flight Center, says fragments of the meteor collected from the ground suggest that the space rock was a rare achondrite, a type of meteoroid created by the melting and recrystallization of larger asteroids.
So we now think we know where that small asteroid that came in over Cleveland on St. Patrick's Day came from. So based on a recent orbit and based on the meteorites people are beginning to find, it looks like that 7-ton rock came from the inner asteroid belt between Mars and Jupiter.
So NASA provides some resources for people who want to hunt for meteorites. We produce a web page here called Meteorite Falls. We produce what's called a strewn field, which is a map of where all the meteorites lie on the ground. They can be anywhere. They could be alongside a road. They can be on top of a building. They can be in a field. When you find these things, you're looking for something glossy, shiny. If it's broken open, the inside of it is kind of a light gray color. And keep them in something soft. You don't want to handle them too much. The meteorite won't hurt you, but the more you handle it, the more you're getting like oils from your fingers and dirt on it. Take pictures of the place where it's found for record keeping purposes, for your own memories, and enjoy it.
The event was followed by reports of another fireball, this time on the west coast above Los Angeles. However, that wasn't a meteor, but the launch of a SpaceX Falcon 9 rocket from the Vandenberg Space Force Base carrying a payload of Starlink broadband satellites into orbit. This is Space Time. And time now for a brief look at some of the other stories making news in science this week with the Science Report. A new study has found that a half-kilometre thick ice dome on the Greenland ice sheet likely melted completely more than 7,000 years ago. The findings, reported in the journal Nature Geoscience, will help researchers better understand how much warming the region can take. By drilling into the proto-dome, scientists were able to collect and test sediments under the ice, and these provide clues to the local climate history. The authors say the top of the sediment likely last saw the sun some 7,100 years ago, suggesting the area was ice-free at the time. Scientists say temperatures were likely around 3 to 5 degrees Celsius warmer around that time than what they are now, and while it's unclear how long the ice dome would take to melt, it's possible that it could melt entirely again if the climate warms back to comparable conditions, which would in turn cause sea levels to rise. Scientists are warning that worsening health impacts from the production of plastics might reach numbers more than double those of 2016 by 2040. A report in the Lancet Medical Journal examined how the global plastics system generates high levels of greenhouse gases, air-polluting particles, and toxic chemicals released from plastic production. The authors model the potential outcomes for plastic production under an unchanged system. Importantly, they say they couldn't assess the potential health impacts associated with the use of plastics, nor the effects of the chemicals contained in plastics, or the health dangers posed by micro and nanoplastics. So instead, they focused on the overall correlation between plastic production and declines in human health. Scientists may have found the region of the human brain responsible for controlling hypocrisy. The discovery, published in the journal Cell Reports, follows efforts by scientists to look for brain regions linked to moral consistency, behaving the same way we expect others to behave. They monitored brain activity in people performing a task that required them to choose between honesty and profit and judge the behaviour of others. They say a region of the brain called the ventral medial prefrontal cortex appeared similarly active in those who judged themselves and others by the same moral standards, while the same region was less active in those whose morals were more inconsistent when they were making their own decisions. In a second experiment, the authors found that stimulating the brain region before the task was linked to more morally consistent behaviour, which they believe is an indication that hypocrisy does have biological mechanisms behind it. If the discovery is confirmed, it could revolutionise the hypocritical comments consistently made by politicians and Hollywood celebrities. A new study claims that some 56% of Americans now believe flying saucers probably exist. Now that's a lot more than the number of Americans who believe in Bigfoot, that's around 28%, the Yeti, 23%, the Loch Ness Monster at 22%, and the Chupacabra at 16%. The study also found that 61% of Democrats and 59% of independents believe in flying saucers and extraterrestrials, compared to just 46% of Republicans. Of those true believers, 30% think unidentified flying objects are probably alien spacecraft or life forms, and 45% believe they have another explanation. 34% of Democrats believe UFOs are probably alien in origin, compared to 26% of Republicans. Of all believers, 30% think unidentified flying objects are probably alien spacecraft or life forms, while 45% believe they have some other explanation, such as black military projects or unexplained natural phenomena. 34% of Democrats believe UFOs are probably alien in origin, compared to just 26% of Republicans. Now, other findings show that nearly half, 47% of Americans, believe aliens have definitely or probably visited the Earth at some point. Democrats are more likely than Republicans to say aliens have visited our planet, 51% compared to 41%, and 16% of Americans think we definitely will or probably will make contact with alien life within the next 10 years. 29% think we'll make contact within the next 50 years, 42% think we'll do so within the next century, and 46% think we'll make contact with alien life within the next 200 years. 73% of Americans, including 75% of Democrats and 72% of Republicans, think that if the United States government did have evidence of UFOs, they'd probably hide it from the public. Only 13% think the government would tell people. The Skeptics' Tim Mendham says the figures present a fascinating snapshot of America's growing belief in extraterrestrial activity.
With the YouGov poll, normally fairly reliable, that most Americans believe aliens exist, and many think that aliens have paid a visit to Earth in recent years. More of them believe it's going to have a negative effect on human civilization than beneficial. I don't doubt the figures. I got no reason to doubt the figures. The question is, why are those figures? And lately, of course, there's been a lot of UFO promotion. Obviously, the presentations to the US Congress and some US congressmen promoting it. It seems like the publicity around Skinwalker Ranch in America. Where
don't forget Chinese weather balloons and
Chinese weather
over in New Jersey.
It's high profile, man. It's probably the highest profile UFOs have been for a long, long time. Therefore, if this is the old story, if it's there a lot, it must be true. But it's there a lot because a lot of people are making the same claims over and over and over again without any evidence. And, a lot of bad evidence does not make good evidence. So in this particular case, Americans are picking up on this plethora of reports, a lot of TV programs, a lot of YouTube videos, a lot of movies, and therefore it becomes this sort of tidal wave of, quote, evidence. And it's not evidence, but it's just a lot of mentioning sort of becomes evidence, and that's obviously the wrong way to go. So, there's a lot of people who believe it, especially, and believers tend to believe it's going to be not good for us, like an invasion. There's not many UFO film stories in which the UFOs are nice.
I guess when you look at the world's history, whenever a more sophisticated civilization comes into contact with a less sophisticated one, it's never good for the underdog, is it?
No, that's right. So that's probably why they see this as being a negative thing, because these people, these aliens, are obviously going to be a bit smarter than we are and a bit more powerful.
That's the Skeptics' Tim Mendham, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.